Good afternoon, everyone, again. I'm Hande Sarantopoulos from the Communications Office. It's a great pleasure to welcome you to our fourth edition of Leaders in Science, the Presidential Lecture Series, a distinguished tradition at Koç University that brings together visionary scientists and thought leaders whose work is shaping the future of research and innovation. Curated and hosted by our president, Profesörü Sitti, this series continues to highlight pioneers at the forefront of their fields, fostering meaningful dialogue and inspiring our academic community. Today, we're truly honored to host Professor Dr. Aydoğan Özcan, a name that holds a special place in our university's story. He's not only a world-renowned scientist and innovator, but also a longtime friend of Koç University, having joined us on several occasions to share his insights and inspire our community. It's a joy to welcome Professor Özcan to our campus once again, and we look forward to hearing his vision for the future of technology and innovation. Now, to introduce our distinguished speaker, I would like to introduce our president, Professor Dr. Metin Sitti, to the stage, please.
Hi, everyone. It's my great pleasure to introduce our today's presidential lecture series speaker, Professor Aydoğan Özcan. Very briefly, he's now currently Chancellor's Professor and the Volgenau Chair for Engineering and Innovation at UCLA. Also, he's Associate Director of the California NanoSystems Institute and a Howard Hughes Medical Institute Professor. So very importantly, just last week, he became one of the National Academy of Engineering members, which is a great honor, maybe the greatest honor for an engineer in the United States. So let's congratulate him for receiving such a distinction. So I received it last year, and it's great to see one new Turkish member receiving this year. So we wish the best for the rest of his career. And he is also a member of our board of trustees, which is very important. He has been with us for a while. And even more importantly, he was the first recipient of the Rahmi Koç Medal of Science in 2016. So I know him for a while. So he got his degree, undergrad degree at Bill University, Electrical Engineering. And then he did a PhD at Stanford. And he was a postdoc at Harvard Medical School. And then joined to UCLA since then. So he has a lot of great research interests, but what I can say is his research stands at intersectional artificial intelligence, optics, and bioengineering, and revolutionizing the fields of computational microscopy and sensing. So we will see his lecture in detail, but I would say I'm very excited to see his lot of progress in this field, and also not only top research, but also seeing innovation and also startup activities out of these great research activities. So in that sense, let's welcome him as our fourth speaker, and look forward to hearing his great speech today. So thank you.
All right, so a lot of friends, a lot of memories at Koç University. So thanks for coming. So it's my great pleasure to be here and share some of the work that we've been doing at UCLA. But first, I have to say a huge congratulations to you, the students, the faculty, the administrators of Koç University. You've done an amazing work. As far as I remember from the first day of my appointment at the Board of Trustees, I'm super impressed every year, despite all the challenges that we have seen globally and certainly in Turkey. You've done an amazing job, and I think we're on a path to recovery, and having seen some of the faculty today, students today, I'm very pleased the upward momentum that I'm feeling. That's very important. So what you guys are doing are amazing. With all the limitations of our current state, your research speaks for itself. So I'm really impressed. So thank you. So today I'll share with you the work that I've been doing at UCLA for about 20 years now. at the intersection of computation, microscopy, and sensing. So my lab is interested in computational imaging techniques. In a nutshell, we want to democratize advanced measurement tools so that whatever you have in your labs, a microscope, a sensor, could be miniaturized, could be made cost-effective to work in resource-limited settings. What I share with you on this slide are some of these devices, technologies that we have been working at UCLA for about 20 years. Some of these are mobile phone-based microscopy tools. We were one of the first groups to convert a cell phone camera into a sensor, into a microscope, high-end microscope. And sometimes we create attachments to the smartphones for microscopy purposes, but sometimes we also take out these CMOS imagers, 5-10 megapixel imager at the back of your camera phone. We sometimes take those out and create standalone microscopy tools like the ones that you see on my right. Those are computational lensless microscopes that can look at a very large sample field of view. This kind of research came a long way. Maybe 15 years ago, your smartphone didn't exist. Cell phones were barely having a camera, maybe 0.5 megapixel. And with those kinds of cameras, we were building microscopes that you see here on this corner. That wasn't a smartphone. You could barely see a red blood cell with that. A red blood cell is about 7 microns in diameter. You could barely see a red blood cell, but soon the technology advanced so much that with our smartphone-based microscopes, we could see even DNA molecules. This is a fluorescence and dark field microscope attached inexpensively at the back of a smartphone camera, and you can see nanoparticles that would normally take a high-end microscope to visualize with just a smartphone-based imaging system. These are fluorescently tagged nanoparticles. In fact, you can tag individual viruses with a few hundred fluorophores and start sensitively and specifically count the viral load of a patient with a smartphone-based microscope. These are cell phone-based human cytomegaloviruses that are individually labeled, again with a few hundred fluorophores per diffraction-limited spot size, that are giving you those beautiful cell phone-based microscopic images of viruses. On the right-hand side, you see a confocal microscope. That's a high-end benchtop microscopy tool that gives you kind of like the same kind of information, but of course, much more expensively and not portable. You can also even see a DNA molecule. This is a double-stranded DNA molecule that is stretched on a glass surface with very simple silane chemistry. With intercalating dyes, you could size and detect individual DNA molecules with about a kilobase pair sizing accuracy, sufficient for you to understand, for example, replication of certain genes giving you drug resistance for TB and malaria. So it's really come a long way with the evolution of smartphones. These kinds of mobile microscopy tools, all the way from seeing tens of microns of cells, it went down to a DNA molecule size and be able to accurately size it. In addition to microscopy, in addition to imaging small things, we're very interested in using the smartphone for sensing, for replacing some of the sensors that we use in diagnostics labs or microbiology labs. Here you see some of these devices that are using the smartphone as the basis of a quantitative sensor for looking into, for example, bacteria, E. coli, or waterborne pathogens that can be, through some labeling strategies, detected within 10-15 minutes of sample preparation. Some of these devices have been commercialized by startups that I co-founded. For example, this is a diagnostic test reader that you see in here. It can quantify different kinds of lateral flow tests. These are the paper-based tests that are quantitative. We can quantify, for example, a biomarker down to picogram per mil level of sensitivity thanks to the imaging system at the back of the camera phone, so that you can actually administer some of these tests in 15 minutes and read out the results using the mobile phone, as opposed to using lab-based measurement devices. So, as I've emphasized, the mobile phone provided us an opportunity to democratize advanced measurements technologies. And certainly that was amazing for all the way from microscopy to nanoscale to see that evolution. But some of these devices are not running on smartphones, as I show you on the right side here. Those are lensless microscopes that share one common component that is very important for a cell phone camera, and that is a CMOS imager. If you look at one of those devices, that's a lensless microscope where the main component is borrowed from a cell phone. That's the 510 megapixel imager. The main component of this device is a CMOS imager, and the sample goes right above it. We call these kinds of microscopes on-chip microscopes because the sample sits on top of that CMOS imager. There's no magnification lens, there's no objective lens, and everything is computationally working. At the heart of this technology is what we call pixel super resolution algorithms, which means we take images that are sequentially shifted and reconstruct through that a higher resolution image as shown in this movie. In fact, this pixel super resolution technology also works in security cameras. For example, if a single frame is low resolution, but there are multiple frames that are slightly shifted with respect to each other, you can take maybe 10, 20 of those frames and synthesize a higher resolution image of the face of the person. We're doing exactly the same thing, except nothing is moving. Here, different LEDs are digitally turned on and off, shifting the holographic shadows of the specimen on a CMOS imager. So everything is computationally improving the resolution so that we can see fringes, we can see information at the interference of light that was normally washed away because of the pixel size of these CMOS imagers. Stated differently, through computation, we can take, for example, a 10 megapixel imager and convert that into 500 million to 1 billion pixel imager. So all of a sudden you can do gigapixel level microscopy using an inexpensive technology that's field portable and compact. That chip over there on the top, that's a Sony sensor. That is at the heart of a lot of the early generations of smartphone cameras. The green area there is the active area. It's about 20, 30 millimeters square, within which we can do diffraction limited imaging. We can resolve deeply submicron features compared to the pixel pitch. And stated differently, that 10, 20 megapixel imager works for us approximately as a 1 billion pixel system. And that gives us a compact microscope that can resolve features over a very large area, despite being inexpensive, field portable. As you can see, it's as tall as an iPhone and lighter than typically maybe a few hundred grams. One of the first applications that we looked for these types of lens-free computational microscopes was to look for blood smears, to look for signatures of malaria. What I show on the right-hand side, these are red blood cells that are infected with malaria. For example, this cell here, the pink, is Giemsa-stained malaria parasite invading a red blood cell. If you want to diagnose a malaria-positive patient or follow the treatment, you need to count parasites. That's why it's not just for diagnostics, but also for understanding drug resistance. This is still the gold standard. In the middle here, I'm showing you a computationally reconstructed lensless image of the same red blood cells, giving you the beautiful signature of the parasite invasion. However, you can do this across a very large area. This is a thin smear. Most of what you see are red blood cells. Some of them are white blood cells. You can zoom in and reveal the parasite count. Great for peristemia. You can also look at thin sections of tissue for pathology services. This is a thin section, 3-4 microns thick tissue, placed on a CMOS imager, same thing that your cell phones have, and over a very large field of view, you are able to see features at the subcellular level. Traditional light microscopy tools would be looking at those small white squares. At any time you have an objective lens, you have to scan the whole slide to capture this. On-chip microscopy has the throughput and resolution at the same time. We say it has a larger, significantly larger space bandwidth product. You can also bring color and look at H&E stained tissue sections. H&E is a stain that is frequently used in pathology. More than 90% of all human sections are stained with H&E. And what you're seeing here is a lensless microscopic image over a very large area created by these inexpensive microscopes. You can zoom in and reveal these subcellular features with these inexpensive microscopes. Literally, everything that I've shown you so far was captured with a cell phone CMOS imager. Very inexpensive thanks to economies of scale. Those CMOS images are inexpensive just because of the hundreds of millions of cell phone users that we have. They're very advanced, but they're also very inexpensive. But you don't have to restrict yourself just to CMOS technology. What I show here is a CCD, charge-coupled device, which gives you an enormous active area. If you look at the scale bar there, it's a centimeter. You can do microscopy over almost as large as your palm, about 20 centimeters square, sometimes 30 centimeters square, depending on the CCD format. That means you can do extreme throughput imaging, find a needle in a haystack, and solve those kinds of major problems. And very importantly, lensless microscopy does not have this traditional trade-off between resolution and field of view. Every time you want to go after higher resolution, smaller and smaller features, you have to sacrifice the volume that you're looking at. That doesn't apply to cell phone-based lensless microscopy. If you have more megapixels, smaller pixel size, or same pixel size, you can retain your resolution the same and improve your field of view. Those two quantities are not related. That's why we loved the race of megapixel counts in cell phone cameras, because that was driving higher resolution, higher throughput microscopy for lensless imaging. All of this effort is not just making microscopy great again. I don't like that word, but anyways. So it's also making microscopy democratized, inexpensive, higher throughput, yes, but it also enables us to see patterns, to reveal patterns that were very difficult, if not impossible, to see before. I'll give you a great example of that. The problem here that we're going to be tackling with lensless microscopy on a chip is to look at microsumers in a volume that is 3 orders of magnitude wider, larger in terms of nanoliters that we're seeing. Here we're going to be looking at sperm cells as they're moving around without any restriction over a very large area with a thickness of about, a pool thickness of about 0.5 millimeter. As they're moving around, we'll be tracking their locomotion in 3D with submicron localization accuracy. And we're going to do this without any lenses, with just a CMOS imager and 2 LEDs. One red LED, oblique, vertical, and one blue LED, oblique, 45 degree. So you might be thinking, okay, you will get 2 different holographic shadows at the same time, so you must be using a color imager, color CMOS imager, because you're using wavelength diversity. In reality, here we're using a monochrome sensor. It's colorblind. We're using blue and red for 2 different perspectives that are simultaneously on to understand computationally different perspectives. Raw images look like those holograms that are moving around. Sperms are moving around, and very much like watching a soccer game in the night. Every player will have a few different shadows depending on the illumination source. It's the same thing here. Every sperm has 2 shadows, holographic shadows, at the same time. However, it's colorblind. It's a monochrome sensor. You don't know which one is green, which one is blue. Since I know the wavelengths of those 2, computationally, I can plug in the correct wavelength angle combination and retrieve the vertical perspective, erasing everything else, and the oblique perspective, erasing everything else. So digitally, we can look at the same crowded volume from two different perspectives. The rest is triangulation. You know the vertical perspective, you know the oblique perspective, the 45 degrees. You triangulate to find the center of mass of the sperm head. That's how we use monochrome and simultaneous red and blue illumination. From these triangulations, we can track across a couple of hours thousands of sperm cells in 3D and reveal extremely rare events. This one is a human sperm conducting a helix. Color represents time. The black thing is a sperm head. The sperm is conducting a beautiful, tight helix. The top video on the top right, that is the front view. So it's about 2 to 3 microns, 1 second of its evolution. So it's doing a rapid, tight helical pattern. This happens 4 to 5% of the time. You needed the throughput to find these rare helical trajectories of human sperm. Here is another one. This is a hyperactivated human sperm. It happens even more rarely. It's still a beautiful helix, but bigger and irregular circles. If you ever wondered what went wrong with your siblings, perhaps this is the answer. We call it hyperactivated for a reason. So before the cells die out, we can observe thousands of them and reveal all the statistics about these sperm cells. How fast they move, what is their curvilinear velocity, this and that. Funny thing is this, on the far right here, we're showing that 90% of these helical movements were right-handed. Only 10%, 96 out of almost 1,000, were left-handed. So you can actually reveal amazingly rare events, and count them and calculate them. The coincidence here is this. The funny coincidence is that the ratio of right-handedness on Earth versus left-handedness is also 90 to 10%. So there's no coincidence, but it's a very interesting observation that kind of makes you think again up in the night once you realize that the ratio of the right-handed helical motions to left-handed ones were also, again, 90 to 10%. These are animal sperms that we looked at with the same platform. It's a unique platform, not just simple, inexpensive. It's actually revealing with enormous precision, extremely rare events. This is a helical ribbon coming from a stallion horse. So it's doing a zigzag pattern on a plane, but the plane itself is beautifully curving like a ribbon. Color is time. I'll fast forward it just to give you the perspective of this beautiful, precise locomotion. So again, these happen in vitro extremely rarely. We do not know when, under what conditions, they select this motion to another one, but these are enabled by the precision and extreme throughput of lensless on-chip microscopy. This is another one. This is a twisted ribbon, also from a stallion. So basically, it's the same zigzag locomotion per plane, but the plane is twisting like the DNA ribbon. And this is also extremely rarely happening. So the next one is my favorite. This one is coming from bovine sperm, imaged also with a lensless on-chip microscope. Again, enabled by CMOS technology thanks to smartphones. You have more information here, and it's very peculiarly complicated. The blue is the flagellum. It's beating extremely rapidly, reconstructed by triangulation trick that I've explained. Black dot is a sperm's head, and you might be at this point wondering, what is that red, green, and orange that construct? What does it symbolize? Well, that is the local coordinate system on the sperm head. The sperm here is having a head spin. Very much like a screwdriver, it's rotating around its own axis. This was the first time that a sperm was caught having this sperm head spin in a freely moving environment. These kinds of observations for sperms under a microscope would normally be done by immobilizing the sperm head on a glass slide so that the microscope can focus on the volume. This is freely moving and for the first time retrieved in 3D with the sperm head spin. There's some beautiful precision in this motion. With two different angles, we can understand how it's rotating with what kind of an angular velocity it has. So these are some examples of how we use computation to democratize measurement tools, making them high resolution, high throughput, enabling new observations that were not possible before. It's just not simplicity, it's also beautiful, elegant data that we retrieve from these simple systems. My lab is also very interested in applying AI in specific deep learning to enhance microscopic imaging tools. But here we're not interested in classification of images or segmentation of features. We are instead interested in using the function approximation power of networks, neural networks, for reconstructing images, transforming images. For this task, networks are beautiful, and the biggest advantage of a neural network that is trained for image reconstruction is that it's an extremely rapid, non-iterative solution to my image reconstruction task. Most of what I've shown you before, it took us a long computational routine to get to those results. That changed with neural networks. We brought speed, quality at the same time to our reconstruction engine. That enabled us to empower our mobile microscopy tools with an amazing framework that takes a simple laptop and makes use of the GPU in real time to perform very complicated reconstructions that would normally take maybe hours for us to do after the image acquisition. For example, here you see some of our devices, field portable measurement devices, that are powered by AI. Let me show you this imaging cytometer. This shoebox here, this shoebox here is a very inexpensive lensless holographic system. It works based on the same principles that I've described. However, this is a label-free imaging cytometer. That means it can look at micron-sized small particles, cells, as they're flowing through a liquid without stopping the liquid and without labeling anything. It's a label-free, chemistry-free cytometer. And you can use deep neural networks to reconstruct these images in real time. This is actually commercialized by a startup company that I co-founded in 2016. These are commercial versions of the device. What you see in those movies, as we're flowing a liquid sample at a throughput of 0.5 liter per hour, enormous volume, 0.5 liter per hour, and you can actually in real time detect, reconstruct, and show particles, microplastics, algae, you name it. In the previous slide, all of these are plankton that we captured from Los Angeles coastal line, and these were imaged as they're flowing through with a speed of about 1 centimeter per second. Rapid locomotion or motion of the particles, and you get beautiful microscopic imaging. Not just counting size, not just counting concentration. You can also label them, understand what you're imaging, because it's also a microscope. It's an imaging cytometer. And you can do this in the field setting. And one of the applications that we're chasing right now is to understand algae blooms. Algae blooms create a lot of loss every year. And because of global warming, it's getting worse. You can lose a few $100 million in just a couple of days because the bloom kills fish. And that hurts fishermen and all the farms. That's why monitoring 24/7 the quality of the water and counting these small plankton or algae in real time or with some period is very, very important. This is another application of lensless microscopy powered by deep learning. It's for air quality monitoring. You have a nozzle at the top. That's an inlet. It takes about 13 liters per minute in. So within half a minute, you have 6-7 liters of air sampled and deposited on a transparent glass slide. We image before and after we intake, and this way you have a label-free sensor that's working based on color and spatial features and size to reveal what you're breathing in. Especially important for detection of pollen and mold, because let's say you have flooding in this building. What do you do to understand if you have mold? Something like black mold. Well, you send an inspector, they sample different parts of this building, and they send it for culture. This way, with this technology, you can actually do this almost in real time based on the signatures of mold spores. We've shown that you can be actually more than 94% accurate based on shape, color of these particles that are captured with these lenses, field portable devices. We've also moved this technology inside an incubator. How many of you have used an incubator before? Great. So incubators are great, but they're different than microscopes. You take your sample from an incubator after a day, after a week, and you look under a microscope. We have taken our field portable microscopes inside an incubator and coupled them with AI to understand viral replication processes without a microbiologist. Which means this device, as it's scanning right now, it's scanning every well as a function of time. Every well contains cells, and if there is a viral particle there, it's going to kill those cells slowly. Some of them will be killed in a couple of days. Some of them will be killed in a week. You need to quantify it, because that is what we call plaque-forming unit, PFE unit, which means that virus particle is infectious. It can really kill cells. We've shown that by time-lapse imaging within the incubator, without opening the incubator, you can understand PFU count specifically and sensitively much before the ground truth incubation period. For example, this is a VSV that normally it takes 48 hours for those cells to die. We can cut down the time by more than twofold. In under 20 hours, we can sensitively detect the formation of those plaque-forming units. Because of time-lapse imaging, we can understand very, very small changes in the refractive index of the cell because of this virus replication within the cell. Label-free, within the incubator, no need for a microbiologist, AI-powered. It also works beautifully well for other types of viruses. This is herpes simplex virus HSV-1. Normally, it takes 120 hours. So you place it inside the incubator 120 hours later. You take it out, you stain it, you count the dead cell regions. You can do this perhaps about 60 hours, cutting down the time by half without the need for staining or microbiology. Some other examples are shown here. So this was the first line of success that AI helped us achieve. Improve our reconstruction engines for sensing, for microscopy, for specific tasks. In all of these examples that I've shared with you, the teacher for AI to learn, the ground truth, the teacher, was physics. Physics-based reconstruction modules were used as the ground truth for us to teach neural networks how to reconstruct, how to sense. This was the first line of success. Learning from physics so that we understand what we're doing, what we're approximating. But that was the beginning. Soon enough, we realized an even a bigger opportunity, and that is approximating functions that we do not know if they exist or not. So there's no teacher now. Physics cannot help you here, because I'm going to formulate functions, f, that I do not know how to physically write, express. So approximating unknown functions through supervised learning or through image data, that's a huge opportunity, and arguably, in my opinion, one of the biggest impacts that AI had for microscopy field. I'll give you a very specific example so that you kind of can follow me. Let's say at the input I have fluorescence microscopic image of a sample. Okay, I want to transform it into a bright field equivalent microscopic image. Our physical understanding of light-matter interactions cannot help us. I cannot write any function for a forward model between fluorescence and bright field. We're hopeless. Well, that's very difficult. But as if this is not enough, the inputs are label-free, and I want them to be in the bright field channel at the output, but of the labeled version. So the sample is going to also go through a transformation. As if microscopy modality change is not enough of a challenge, the sample is going to be a different sample. Label-free at the input, labeled at the output. Those kinds of transformations can be learned and repeatedly applied in microscopy. Everybody here is lost, and they're asking, who cares? Why should I ever care for a function like that, right? Well, if I can implement that function f, I can change the way that I do histology, pathology, and digital pathology forever. So it's really going to be transformative if I can do that f function. For the last 2 centuries, literally, whenever we take a biopsy from a patient, we thin section it. And if you just thin section it 3-4 microns, look under a bright field microscope, you see no contrast. It's like glass. That's the reason why we invented literally hundreds, if not thousands of stains, so that under a microscope, a diagnostician can look at the same sample, biopsy tissue, and reveal some contrast sufficient for us to understand pathology. That process is a chemical process. It's tedious. Sometimes it takes a couple of hours. Sometimes it takes 24 hours. It's costly. And we don't have always the expertise to do that. What if I could change the entire histochemical staining process and replace it with a neural network that takes autofluorescence, grayscale images at the input, label-free, and transform them as if they're coming from histology labs, entirely bypassing the process. These kinds of supervised learning approaches require you to work with a histology lab. That is your ground truth. You sample label-free tissue, you image it with your autofluorescence contrast, no exogenous fluorescence, everything is endogenous. Samples go to a histology lab, they create a ground truth for us, and we learn that transformation by pairing these images. In terms of the technology, AI technology, for those who are more familiar with the CS side of things, yeah, I like diffusion models and I use them. Brownian bridge diffusion models are one of my favorites. They're slower, they're good, but my ultimate favorite is still, again, generated addition network, which means there are 2 different networks that are fighting with each other. You can think of the generator there, the blue, as the painter, micro-painter of tissue. The discriminator is the critique. It's a game theoric approach. Nobody wins, which means I have a beautiful generator at the end of the learning process, which means a discriminator with 50% confidence will not be able to tell the difference between approximately histochemically stained and virtually stained imaging. So learning is a one-time effort. It can take weeks depending on the availability of tissue and ground truth. But once you train it, we fix the generator. Now, everything that I'll share with you in the next few slides, it's blind testing. That means learning is finished, generator is fixed, it's in my pocket, and I tested with new patients never seen before. These are some initial examples from H&E stain. One of the most frequently used stain in pathology is H&E. And what you see here on my right, these are inputs. They're contrast enhanced per your eye. It's not one of those generated models where you have noise input and garbage input and beautiful hallucination output. No. These are conditioned generative models, which means inputs are diffraction limited microscopy images. Without that, it doesn't work. So you must have beautiful contrast and resolution at the input, which we do. At the output, you see the AI's output versus what comes out of histology after 2 hours. A good H&E would take 2 hours of a histechnologist, the human person who stains tissue. It doesn't only work for simple stains like H&E. This is a different stain type, Jones silver stain. It takes 3 hours for his technologist to stain this. That's why it's 10 times more expensive per patient. At UCLA, this is 10 times more expensive than H&E. And you can see beautiful match with respect to what comes out of histology, except in less than a minute you get the result virtually, without any chemicals, without any humans involved. Some other organs, some other stain types. All in all, it saves us time. You can multiplex, and there are so many important advantages of this technology. And here, I'm sharing also the fact that it can do immunohistochemical stains. IHC, immunohistochemical stain, is an antibody antigen-specific stain. It takes 24 hours typically because this is taking a while for the binding to happen. So there's a good amount of incubation time. Here you're looking at HER2 stain. It's a very important stain for breast cancer patients. Some breast cancer patients overexpress HER2 protein at their membrane, cell membrane, and this brown color here is representing that overexpression. Some patients are zero, HER2 zero, and that's very important because if you're HER2 zero or 2+ or 3+, you have different treatments. This would be normally taking 24 hours, and here you can take in minutes the same kind of images from autofluorescence contrast. These were examples of how you create an image and compare it to standard of care from histology labs. But that's not enough for a pathologist. You need to also give them these images and ask them to diagnose the patient. Can you diagnose correctly the patient's condition with our images versus with standard of care, with the traditional histochemical staining? The answer is yes. We have created these kinds of comparisons. A single sentence summary: we've passed the pathologist Turing test, which means they cannot tell the difference between our images and standard of care. And they can do the same things that they're accustomed to doing with the standard images using virtual staining. But there are many advantages. One of the most important advantages of virtual staining is standardization. Look at these images on my right. They're standard H&E coming from UCLA histology. You see the variations from patient to patient, right? That's bad. Diagnosticians don't like that. AI also doesn't like that, downstream AI. Look at the virtual staining results. Consistent. Consistency is very important for pathologists and AI to look at these images to augment the diagnostician's decisions. Arguably, the biggest advantage of virtual staining is multiplexing. That means from a single image, autofluorescence signature of the same region of interest, I can create a panel of stains that are nanoscopically registered. That's not possible today. If you want to create a panel of stains from a tissue block, you deplete tissue. Think of it like a potato chip, right? You cut the potato to create those thin sections and you're done. The potato is gone. Every time someone is called for a secondary biopsy, if you want to understand what's going on, they depleted your tissue by staining. And virtual staining does not deplete tissue. That's very important for spatially small animal experiments because the organs are tiny. You need to do more with your stains. So we've also done this with in vivo virtual staining. Without taking a biopsy, we can actually use a confocal microscope and look through the skin and give you virtual biopsy using a device called the reflectance confocal microscope, which is an FDA-cleared device for dermatopathology use. I'll finish up with a very important question by answering a very important question. AI is cool. It looks very powerful. You can potentially save some time, money, and multiplex and save tissue. But hey, what if AI hallucinates? What if AI hallucinates? What are you going to do? Well, that's a very important and major concern. All forms of AI will hallucinate, and you will need gatekeepers to work with AI in medicine. The real problem for virtual staining technology from the perspective of hallucinations is realistic hallucinations. Unrealistic hallucinations are not important. Unrealistic artifacts happen all the time in histology today. For example, look at that folded histology on the far right. That happens because of tissue processing artifact. Diagnosticians don't care about that. They understand it's an artifact. They move on to another region of interest. doesn't bother them. Virtual staining can also create unrealistic hallucinations that diagnosticians will just laugh at it and then they will move on. Nobody will be misled. Look at that, for example. The green color in Mason's trichrome that we hallucinated was created by a dust particle, a plastic most likely, that was seated on tissue. It gave us an out-of-distribution autofluorescence. We hallucinated, but nobody is having a problem with that because that hallucination is so obvious because Mason's trichrome doesn't have that color. AI hallucination problems are not issues if they are easy for diagnosticians to spot, and they are called unrealistic hallucinations, and today's pathology already have a lot of these. The real danger is realistic tissue hallucination. What does that mean? It means something very simple. I'm the patient, patient A. I give my biopsy. It's stained by a virtual staining model, but it converts my tissue into patient B. That never existed. But patient B's virtual stained image looks perfect. From the perspective of a diagnostician, a pathologist, it's going to be looking like, oh, it's beautifully stained. But it's taking a disease state and changing it to something else, perhaps benign. Those are not easy to spot because realistic tissue hallucinations, because AI is so powerful, they will be interpretable by experts. Pathologists would like what they see. They will look like plausible patients. That patient B that's hallucinated in terms of tissue never lived, but would look like a completely plausible, perfect patient. And the diagnostician will say, this is a very good stain, slight, benign, and I'm ready to sign my report. Except, hey, I'm the patient here, and I have a problem. I'm not benign, right? So these are the most dangerous forms of hallucinations. And the question is, autonomously, without ground truth, I'm replacing the ground truth. There's no histology left in the future, let's say. Without ground truth, without having histology, how do you understand these hallucinations? And not only autonomously, but also without access to the model. I'm the hospital. I won't share my model with you. I'm making money off of it. So you have no access to my model. You cannot quantify its uncertainty. And you don't have the ground truth. The only way out of this paradigm is to connect virtual staining with the raw data. If you only give me virtual staining results, you would toast. Generative AI will create new patients. Nothing can save you from that, with some probability. However, if you also give me, with every virtual staining result, if you also give me the raw measurement, I can actually understand consistency between my measurements and your output. And for that consistency, we call it physics consistency, I don't need to know your model. I don't need to know the ground truth. So it's autonomous, model-free. We quantify uncertainty. And the only way out of this is when I do gatekeeping, quality assurance, I must have your output and I must have your physical measurement. If you attack the virtual staining result, I will understand it because the fingerprint of the patient is the autofluorescence in this case. This has been very powerful. I'll finish off by showing you the bottom part here, part C. This is showing you how bad diagnosticians are in understanding AI hallucinations. As an evil exercise, we created poor virtual staining models. Purposely, we created poor models. We knew that they would hallucinate. A group of diagnosticians looked at the quality. X-axis here is coming from the average of a group of diagnosticians. All of these images here were bad, coming from purposely created evil models. They passed a lot of them. Yes, some of them they caught. These are unrealistic hallucinations, and that's why they were caught and stopped by the diagnostician. They said, I won't write my report on these. But everything on the yellow part, we fooled them. By looking at physics consistency, all of them were autonomously caught. So diagnosticians are clueless. They don't understand the hallucination potential and the new created image. By looking at autofluorescence mismatch, the fingerprint mismatch, we were able to catch them without access to the model without access to the ground truth, autonomously. So all in all, virtual staining is very powerful. It saves labor and time, reagents. Some of these stains would take 24 hours. You can cut down a significant amount of time and create a panel of stains from the same cross-section, which is extremely important for pharmacology-related, toxicology-related studies. In fact, this is also my conflict of interest disclosure. In 2019, I co-founded Pictor Labs as a spin-off from my lab at UCLA. Pictor in Latin means painter, and we're painting microstructure of tissue. That's how I was opening, during the pandemic, my VC pitches. So Pictor Labs now raised about $50 million, and I'll leave you off with a professional model that's going to start with autofluorescence. This is a Pictor Labs model. Autofluorescence at the whole slide level. We rapidly bring in H&E. The diagnostician can zoom in and then bring an immunohistochemical stain, PEN-CK. It's very important for cancer-related diagnostics. So the brown is coming, that's PEN-CK. That would normally take 24 hours, and you cannot do it on the same tissue. That's for the first time multiplexing. And if you want, you can bring a third, fourth stain. Soon you're going to see Mason's trichome coming from the right. So this is my final slide. Thank you very much for having me, and I'd be happy to answer any of your questions. Thank you.